scholars were awarded. Sir has presented more than 50 research papers in journals, 10 in edited books, 7 in conference proceedings, 44 in seminars, and also completed 5 books, which is great contribution to the society. Sir has delivered more than 75 special lectures as a resource person. Dr. Mahesh is a member of Faculty of Arts, Board of Examination, Chairperson, as well as Board of Examination in Mangalore University, Karnataka University, Sri Vijayanagara Krishnadevaraya University, and various places. Sir is also member of Academic Council, JSS College for Women, Board of Studies, West Asian Studies, BOE in Development Studies, University of Mysuru. We are really blessed to have you in our midst, sir. Over to you.
Chetan? Chetan?
Yes, sir. Yes, sir. Yes, sir.
Okay, sir again rejoined now, so made him as a co-host.
Okay, sir. Okay, sir. Yeah, Maheshwar is now the co-host, sir.
Yes, yes, sir. Sir, you can unmute yourself, sir. Sir. Sir, you can unmute yourself, sir.
Okay, good morning. Yeah. Okay, thank you. So now I hope I'm audible.
Yes, sir. Yes, sir.
Okay. So, okay, good morning to one and all. Dr. Uchegowda, sir, and all the faculty members of Department of Economics, Davangere University, and all the participants. I express my gratitude to my gratitude to the Department of Economics and all the professors, including Professor Rangappa sir, Suchitra ma'am, Selvi, provide this opportunity to share my knowledge with you in this morning. The topic given for me is the topic related to application of statistical tools, and more specifically related to a discussion on parametric and non-parametric tests. But one minute, I have some issue related to video, because the video is not working. Only probably you are hearing my voice, but I have a problem related to video. Okay, June is unable to detect your camera. Okay, 1 minute please, I will correct and I will join. Probably it is whether the screen is sharing, Professor Uchegowda sir? Hello?
The screen is visible, sir.
Screen is visible?
Yes, sir. The screen is visible, sir.
Yes, sir.
Okay, but okay, 1 minute.
Now even the PPT is visible, sir. Yes, sir. Yes, sir. PPT is visible, sir.
Okay. Okay, thank you. Once again, good morning to you all. The topic which I here taken for my discussion is the parametric and non-parametric tests. Before getting to this parametric and non-parametric test, all of us as the researchers and using statistical tools for analysis of our collected data, we should have to have some basic knowledge regarding the selection of the statistical technique or tool which should be appropriate related to our research problem in general, or more specifically the objective of our research work or the research question. So hence, let me start my lecture with choosing the statistical technique which is appropriate. Then I will come to the parametric and non-parametric test, and we will have a brief discussion on the most popular parametric and non-parametric test in its simplest form. As all of us knew that as researchers, we should have to select a statistical tool, as just I have mentioned, based on the research question of our topic or the hypothesis being constructed and expected to test that hypothesis using the statistical tool. So hence, the first criterion to the selection of or choosing the statistical technique is the specific research question under our consideration or the hypothesis being tested. So based on that hypothesis, then we should have to determine the number of the variables in the question, because the statistical tools which are proposed and developed by the statisticians to analyze the data are based on the number of the variables we have chosen. Generally, statistical tools available for data analysis are classified into three categories based on the number of the variables in question. Like the first one is the univariate statistical tools, that is called as univariate analysis. The second one is bivariate analysis, and the third one is multivariate analysis. So these are the three types of analysis which include the statistical tools appropriate for analyzing the data based on the number of the variables. Whereas in case of univariate analysis, we have only one variable, a single variable. Then we have to select a specified type of statistical technique to analyze the single variable. And if we have two variables, and if our purpose is to compare the difference between the two variables, or to measure the association between the two variables, or so on, then we have to select the tools related to bivariate analysis. And if the number of the variables in our research question are in a hypothesis is more than three variables, three or more than three variables, then we have to use the statistical tools come under the multivariate analysis. So hence, the second important criterion in selection of a suitable statistical tool is the number of the variables. So we can classify the statistical tools based on that number of variables as univariate statistical tools, bivariate statistical tools, and multivariate statistical tools. So once we have decided the number of the variables in our research question or hypothesis, the third stage to select an appropriate statistical tool is to determine the level of measurement of the variable or variables. That is, the variables are classified, measured into different types or in different forms. Probably all of us, we read or heard, and even in our previous sessions in this course, you have studied that or learned that broadly the variables of our research work are classified into quantitative variables and qualitative variables. This is one of the broad classifications. Then the second one is, again, we can classify the variables as discrete variables and continuous variables. The one more classification is based on the time period. We can classify our data as cross-sectional type of data, time series type of data, and pooled or panel data. This is the other type of classification. But the most important, because in most of the cases, the selection of a statistical tool in any research work is based on the classification of the variables based on its measurement. So there are four types come under this measurement of the variables in statistics. They are called nominal variables, ordinal variable, interval variable, and the ratio variable, or nominal measurement, ordinal measurement, interval measurement, and ratio measurement. So once we have selected and of course identified or determined the level of measurement, so then the next step is we should have to select a statistical tool, whether in case of univariate method, bivariate method, or even in the multivariate method, whether the purpose of that particular statistical tool is only to describe the statistical characteristics of our data, or to draw conclusion, or to draw inference from the statistical information at our hand. So hence, further, another important criterion is whether we are using this statistical tool, selected statistical tool, for the descriptive purpose or for inferential purpose. So this is another important point which we should have to bear in our mind. So then lastly, so if we have selected a statistical tool for the purpose of draw inference or to conclude about our population characteristics based on the sample evidences. So, or in other words, very simply, if your study is based on the sample evidences, or if you have selected a sample from the population and use statistical tools for estimation of the statistical characteristics based on the sample data, then you have to draw conclusion or inference. That is, whether your sample results are valid or not, whether they are as close as possible to the true values of the population or not. Then we have two methods of that statistical inference or the inferential statistics. The one is the parametric statistical tools. The other one is non-parametric statistical tool. So hence, our discussion in this session, this and the next session, is related to the use of statistics for inferential analysis, for inferential statistics, or to draw inference about our population based on the sample evidences. So these are the things which we should have to bear in our mind as a researcher in choosing the statistical technique or selecting appropriate or suitable statistical technique for our data analysis. So to conclude on this introductory part of my discussion, selection of any statistical tool, choosing any statistical tool that based first on our research question or the hypothesis being tested. So based on that hypothesis being tested, you have to first select the statistical tool. So then the second criterion is the number of the variables in your hypothesis or in your research question. So based on that number of the variables being included in your research question and intend to test the relationship or the impact, whatever you want, or to measure the difference, or to measure the association among your selected variables. Okay. So then we have three tools of statistics, or all the tools of statistics are classified based on this number of the variables as univariate statistical tools, bivariate statistical tools, and multivariate statistical tools. So once you have identified the number of the variables and selected the appropriate statistical tool, so then you should have to determine the measurement of the variable. So here, as we were noted that whether your variable being used for testing or to analyze your data, whether it is a nominal variable or a ordinal variable or a interval or ratio scale variable. But in practice, there is not much difference between interval and the ratio scale variable, because the most of the statistical tools are equally used between this interval and ratio scale. So this is the fourth point which we should have to bear in your mind. So then the next one is, once we have selected or determined the level of the measurement of the variable as ordinal or interval or so on, then we should have to select the statistical tool for the purpose. So for the purpose here means the purpose of use of that particular statistical tool, whether we are using that statistical tool only for the descriptive purposes or for inferential purpose So for example, if your purpose is to use the different descriptive purpose, as all of us knew that the most popular methods of statistics are the tools of statistics are like graphs, tabular representation, measures of central tendencies, measures of dispersion. So even, of course, we can use correlation integration without testing them as the descriptive statistical tools. But if our study is based on the sample, or if you have selected a subset of the population for our study, if we are unable to get information, or if the population is not accessible to us in majority of the cases, as the researchers we noted that our study is based on always the sample evidences. So if our study is based on sample evidences, then the more appropriate statistical branch is inferential statistics. So because by using those tools of inferential statistics, we are able to validate our results. Here the validation means whether our sample values, whether our sample results are in par with the population values or not, whether they are same as the population values or not, whether the estimates means the sample sample values. So whether these sample values are close to the population values or not. So to answer for all these questions, so we have to use these tools of inferential statistics. And of course, these inferential statistics has twin branches. The one is estimation, the other one is hypothesis testing. And there we should have to frame an hypothesis. And of course, in almost all our research works, we have hypothesis. So to test that hypothesis, we have to use the parametric tools or non-parametric tools. So hence, now we have ended with the last classification of these tools, and they are classified in inferential statistics as the parametric statistical tools and non-parametric statistical tools. So before getting to the specific parametric and non-parametric tools, let us again have a brief theoretical discussion or a descriptive type of discussion related to what do we mean by parametric tests and what do we mean by non-parametric tests, or what do you mean by parametric methods and or non-parametric methods. So the parametric tests are restricted to the data That is, they are purely based on the data, and there are some assumptions in use of the parametric methods or parametric tools for testing hypothesis. One among them, or the most important assumption of the parametric test, is that so the variables which we have selected for our analysis are assumed to be normally distributed. Okay, they are showing normal distribution. And I hope all of you have the basic knowledge of those, the statistics and the probability theory, then distributions of probability and so on. And also I hope you have been, I think, observed that shape of that normal distribution, which is a bell-shaped curve. So the selected variables, our chosen variables of our study, assumed to be follow normal distribution. That is the first assumption we can say that should be met to use these parametric tools. The second one is the variables which we have chosen are independent of one another. So that means the variable should not be related. The variable should not be dependent. Okay. So that is the second assumption. Then the third one is, and the most important one is that all these variables are of continuous scale of measurement. So this continuous scale of measurement means, earlier I have told you that they are the interval variables or the ratio scale variables or metric variables, quantitative variables. So these are the synonymous names for that interval, ratio scale variables, or continuous variables, or metric scale variables. So hence, the three important assumptions which are required to use the parametric tests are: the variable should be follows normal distribution. The variables, if you have more than one variable, then the variable should not be dependent on the another related variable, or they are independent to each other. And the third one is the variable should be continuous in nature, or they should be metric in nature, or they should be interval or ratio scale variables. So these are the three important conditions, or we can also say, to use parametric test. Then on the other hand, the non-parametric tests need not to assume the above assumptions, either related to the distribution or related to dependent or independent kind of nature, and also need not to be a continuous scale variables. So hence, if you just observe the three important points below this non-parametric test, so these non-parametric tests are used when the data does not show a normal distribution, or if the selected variable is not normally distributed, you can use non-parametric test. So that's why whether your variable is quantitative or qualitative. So even for a quantitative variable, if that variable not follows the normal distribution, you can use non-parametric test even for the qualitative variable. That is for nominal or ordinal variables. But the reverse is not true. That means we cannot use non-parametric test for the parametric test for the qualitative variables, for the nominal variables, for the ordinal variables. So hence, whether your variable is nominal or ordinal, whether it is interval or the ratio scale variable, if the variable does not follow the normal distribution, then you can use non-parametric test. But if the variable follows the normal distribution, then you can use parametric test, but only for interval and ratio scale variable. This is the difference between the parametric and non-parametric test in terms of its distribution. The second one is, so they might dependent or condition on one another. So the variances, more specifically, of course, we can say that. So the variables can be dependent and conditioned one on another. Even in that situation, also we can use non-parametric test. And the third one, So these non-parametric tests do not have a continuous scale of measurement. Just we have already noted that. So with the variable need not to be a interval variable, need not to be a ratio scale variable. So we can use this non-parametric test for nominal variables, for ordinal variables, and also if the variable is not follows the normal distribution, if it is continuous, even for that continuous variables also we can use non-parametric test. So hence the parametric and non-parametric tests are the kind of test based on some assumptions, more specifically related to parametric tests. So these parametric tests are having some parameters. For example, I hope all of you knew that the parameters of the distribution. For example, the normal distribution. The normal distribution has two parameters. So like mean and the variance or the standard deviation. That's why it is mu and sigma square within the bracket. Probably you have seen as the characteristics of the normal distribution. That's why in case of parametric test, all these tests have some parameters of their respective distributions, because in parametric test we have different distributions. The most popular parametric distributions, all of us knew that they are the normal distribution, t distribution, and f distribution. Okay, these are all the three important parametric distribution. Along with that, there are some other parametric distributions like half normal, or so exponential or uniform distribution, and so on. Okay, but the most popular are the normal distribution, t distribution, and f distribution. These are the three important parameters, because each of these distributions are identified with the parameters, like the two moments of the distribution, one with the mean, the other with the variance. Whereas for non-parametric tests, there is no such parameters. So we need not to identify a parameter, because there in case of non-parametric test, just we have noted that we have not at all assumed the variable follows any specific distribution. Since it does not follow any specific distribution, there is no parameter for them. So hence they are called as non-parametric tests. This is one of the important distinction. The other one is these non-parametric tests are also called as distribution-free tests. So probably you know the meaning why now we are calling this as distribution-free test, because there is no distribution for these non-parametric tests. Hence they are also called as the distribution-free test. Distribution-free test. These are few sentences or few assumptions for parametric test, and there are no such assumptions for the non-parametric test. And we have some more distinctions or the differences between these two. The parametric test, which is information about the population, is completely known, because as already we have noted that these parametric tests are used as a tool in inferential statistics, and in inferential statistics our purpose is to draw conclusion about the population. Hence the information about the population is known to us as one of the characteristic for this parametric test. Whereas for non-parametric test, no information about the population is available, in the sense that so since the distribution is not needed to draw conclusion or inference, so hence the no information is not available, or no information is about the population is available. And the second one is specific assumptions are made regarding the population, just we are noted, and no assumptions in case of non-parametric test. And the null hypothesis is made on parameters of the population, whereas in case of the non-parametric test, the null hypothesis are free from the parameters, any parameters. So that's why, for example, all of you have noted that in testing hypothesis, in using the t-test or in the z-test or in the f-test, for example, testing about the mean as the statistical characteristic, then we were noted that there is no difference between the mean. There is no difference between the mean, or the means of the populations are different as an alternative hypothesis, or the variances of the population is same. So these are the parameters, because the mean is one of the parameter, variance is one of the parameters, skewness is the third parameter. So then the kurtosis is the fourth parameter. So hence every hypothesis in parametric test are stated in terms of the parameter. Our purpose is to test that parameter, whether it is true or not, whether there are association between those parameters or not. But whereas in case of non-parametric test, so the null hypothesis does not have any parameters, or we need not to specify or to state our or to formulate our hypothesis in terms of parameters in case of non-parametric test. Okay. Then the next is again the difference. As just we were noted earlier, in case of parametric test, the test statistic is based on distribution, whereas in case of non-parametric, it is arbitrary. That means we need not to assume any distribution for that. In parametric tests, they are applicable only for the variable, whereas in case of non-parametric tests, they are applicable for variable and attributes. That's why the attributes are the qualitative aspects. Even we can test that qualitative aspect in case of non-parametric test, but we cannot test that qualitative aspect, attributes or characteristics in parametric test. And no parametric test exists for normal scale data, nominal scale data, because so there is no, if our data is nominal scale data, there is no parametric test for that. But we can even test that nominal data, ordinal data using the non-parametric test. And of course, finally, the point which we should have to be bear in our mind, yes, one of the distinction between or the difference between the parametric and non-parametric test is that the parametric tests are more powerful than the non-parametric test. The reason is these parametric tests are based on the measurement, based on the quantitative measurement of the variables. So hence they are more powerful. But whereas this non-parametric tests, they are related to attributes, they are related to the characteristics, they are related to the quality of the variable you have been selected. So hence they are not as powerful as the parametric test. But it doesn't mean that, so we cannot use this non-parametric test in practice, because if you get into the statistics books and the recent developments in statistics, so we have equivalent number of non-parametric tests for every parametric test. So for example, I hope all of you knew one mean test, two means test, like independent sample test, dependent or matched pair test, ANOVA test as the classical hypothesis testing procedure. So for every of these parametric tests of hypothesis, there are equivalent non-parametric tests are available if our variable does not follows the normal distribution, whether it is a quantitative variable or even it is a qualitative variable. So we will look into that in our discussion as the non-parametric text later. So this is again about distinction, difference between non-parametric test, and probably so these differences and the discussion thus far we were had, okay, gives us some idea about so when to use parametric tests and when to use non-parametric tests, and what are the conditions to use parametric and non-parametric tests. So then, before getting to some specific types of tests, here we have one chart. This chart shows us the classification of the hypothesis test as parametric and non-parametric test, and some of the important tests are given as follows. So the hypothesis tests are broadly classified into parametric tests and non-parametric tests. Just we were noted that the parametric tests are based on metric data, numerical data, quantitative data, whereas non-parametric tests are the tests based on non-metric type of data or qualitative type of data or nominal or ordinal data. So the most popular parametric test, of course, again, I have told you that in one of the previous discussion or the slide you have seen that. So based on the number of the variables, if you have only one variable, one sample here in terms of statistical words, if you have only one sample, so the tests which are used to test any hypothesis regarding a single sample is called as one sample test. One sample test. So if you have two variables, then it is two sample tests. If you have more than two variables, of course, that is not given in this slide. If you have more than two samples, then it is called as more than two sample test or K sample test. K refers to number of the variables. K sample test, or in other words, multivariate sample test. Multivariate sample test. So, and also just you are noted that there are four important statistical characteristics of the variable, and they are called as moments of the distribution, and also they are known as characteristics of the distribution. And most of the statistical tools are related to the first two characteristics, and within these first two characteristics, the highest number of the statistical tools are related to the first moment, first characteristics of the data, that is the mean or the average. That's why the first moment is average or the mean, the second one is variance, the third moment or the characteristic is skewness, and the fourth one is kurtosis. So this mean that refers to the average of the distribution. The variance refers to the dispersion or the spreadness of our variable or the observation of the variable, whereas the skewness is related to the shape of the distribution, and the kurtosis again it is related to the shape. So shape, and only we have lesser number of tools in fundamental statistical analysis and their applications related to the last two characteristics, that is the skewness and kurtosis. But if you get into the practice, if our variable not follows the normal distribution, or if it is skewed, so then we should have to use, or we have to correct for that skewedness by using the statistical tools. So that's why here based on our previous discussion in selection of the statistical tool, so if our purpose is to test a hypothesis related to the mean of a single sample or a single population, we have to use a t-test, that is called as one sample t-test. And if we use the z-test for that purpose, then it is called as z-test, one sample z-test. So z-test is based on normal distribution or the standard normal distribution. More specifically, t-test is based on the t-distribution. And the purpose of these two tests is same, but the difference is in terms of the number of the observations. And probably all of you have read and read in statistics is that there is a difference in the number of the observations, and that classified as small sample and the large samples. And again, we can call it as the t-test is a small sample test, whereas the z-test is a large sample test. In pure theoretical point of view, so if the number of the observations are 30 or greater than 30, that is called as a large sample size, and then we have to use a z-test. So if the number of the observations are up to 29 or less than 29 observations, that is called as small sample size, then we have to use t-test, whether it is for one mean test or even for the two means test, which is holds good. And if the number of the variables are 2, then if the variables are, because once we have two variables, then whether the variables are related or not. So if the variables are related, we have to use a separate procedure. If the variables are independent, not related, we have to use a separate procedure for that. So hence, in case of two sample related analysis, bivariate analysis, for testing means of the population, then we have independent sample test and the dependent sample test. The dependent sample test is more popular as paired sample test, matched paired sample test. So if the variables are independent to each other, again we have to continue to use the same t-test and z-test, both in case of independent sample t-test and the paired sample t-test, but the procedure of estimation is different. So along with this, if you have more than two variables, that is 3 or more than 3 variables, for testing a hypothesis related to the mean of the populations. So if you have 3 means, so then you have to use analysis of variance, that is the F-test. ANOVA, probably you have heard that. Similarly, related to the variance, if your purpose is to test about the variance, one variance test, two variance test. For one variance test, we have to use chi-square. For two variance test, we have to use F test. Okay, like that, the second type of analysis in case of parametric test. Whereas in case of non-parametric test, if the number of the variables are only one, which is called as one sample, then we can use chi-square test for one sample, Kolmogorov test, that is called as KS test, run test, binomial test. Okay, these are the tests which are used to test about a single sample or a population. If you have two samples, then we can of course use chi-square test even for the two variables or the two samples. Then non-Whitney test, that is called as MW test, and median test. Case again, case test can be used for one sample and also for two samples. Okay, then chi-square test can also be used for one sample and two samples for the non-parametric type of data. Okay, and if the number of the variables are two but they are dependent paired sample, then we should have to use sign test, Wilcoxon sign test, McNair, chi-square test. Even for paired tests also we can use chi-square. If we have more than two variables, two nominal variables, two ordinal variables, more than two or three or more than three nominal or ordinal variables, again we have some kind of test like a Friedman test, and say that is the case W test we have, okay, like that. So this is a brief discussion related to the classification of the statistical test to test the hypothesis based on parametric in nature and non-parametric in nature, and the fundamental statistical hypothesis tools to test only the mean. Okay, all these are used in case of the mean, and whereas of course in case of non-parametric test the mean is not meaningful, hence there we will have to use the median as a base for testing and comparing and measuring the associations and so on. So this is about a brief discussion on the differences between the parametric test and the non-parametric test. So with this background, so let me continue my discussion first with some fundamental statistical parametric test. What they mean, that is what do we mean by one sample test, how we can test that the hypothesis related to a single population or one sample using the t-test and z-test. Then I will take a discussion on the two sample tests, that is the measuring and the difference between the two population and testing the means of the two populations of independent in nature and dependent in nature. And also we will have a brief discussion on the k-means test, that is called, or using the analysis of variance. Okay, analysis of variance. So now the first of its kind as a base for our development of hypothesis and hypothesis testing is the single mean test, or testing populations, testing mean about the single population, or the single sample mean test. I don't want to get into a detailed discussion on this, because in practice, in our research work, our purpose and also the number of the variables we have in our research work is not only one, not a single variable we have. In majority of the cases, in our research work, we have more than one variable, two or more than two variables, and further our objective is to measure the associations, measure the relationships, and also intend to measure the impact of the one variable on the other related variables, that is to measure the cause and effect type of analysis and so on. So hence this one sample test, single mean test, is rarely used, means only when we required for a specific case we have to use, otherwise so it is not much used in practice. Though it is not much used in practice, but this single mean test provides the base for hypothesis testing regarding the mean. So any other hypothesis test, 2 means test, 3 mean test, or k means test, they are just extension to this 1 mean test or the single mean test. So hence we have a brief discussion on this hypothesis testing regarding a single mean. And in testing a hypothesis for the mean, that is the average, we have again to identify or to determine whether the standard deviation of that population is known or unknown. So the symbol in this slide, that is this one, mu. So this mu is the population mean. Okay, the population mean in statistics is denoted by this symbol. This is mu, and the standard deviation is denoted by sigma. So hence the mu is the population mean, the sigma is the population standard deviation. Okay, so if the population, our purpose is to test the population mean. So if I take an example, let us assume that you have collected, or your purpose is to measure, okay, one of the economic variable, that is the income of the households in one of the city, for example, Mysore. So my purpose is to measure or to estimate the average income of households in Mysore city. In Mysore city, there are 3 lakhs plus households are there. So as a researcher, I am unable to collect the information from these 3 lakhs households. Though it is theoretically possible, because I hope all of you have basic knowledge about population and sample, and why in majority of the cases we rely only on the sample instead of going for collecting data from the population as a whole. I hope you have all those basic knowledge. So hence a researcher practically impossible for him to collect the information from the whole population or each and every object of the population. So okay, hence he has selected a subset of population that is called as sample. So my population, for example, this illustrative example is 3 lakhs households in Mysore city, but I am unable to get into that collection of the data from all the 3 lakhs households. Then I have randomly selected a sample from these 3 lakh households, like 500 households. So then my purpose here is to test or to estimate what is the average income of households in Mysore. I am answering this question or drawing inference about this question by having information from only 500 households. So in this process of validating my results of 500 households, for example, let us assume that I have collected the income of households from 500 families, and the average income per month is 25,000 rupees. This is the sample mean, sample average, that is 500 families average income. But my primary objective, as we were noted that in any research, is to study about the population, 3 lakhs households average income. So whether my estimated value, sample value, that is 25,000 mean or the average income is same as the population value or not. So I need to test this. So that is called as the process of hypothesis testing. I hope you have basic knowledge related to that hypothesis testing. So in that process of hypothesis testing, in case of the single mean test, okay, single mean test, whether the standard deviation is known or unknown. If the standard deviation is known, we have to use Z test. If the standard deviation is not known, we have to use T test. And the earlier case, I have told you that when to use T test and when to use Z test. So based on one of the criterion is based on number of the observations, small sample or the large sample case. The second and the most important theoretical, okay, the reason for selection of Z or the T test or between these two is that is when the sigma is known, The standard deviation of the population is known, we have to use Z test. If the population standard deviation is not known, then we have to estimate the standard deviation of the population from its estimate. That is sample standard deviation, it is called. So if we use the sample standard deviation in our formula or in our method of estimation, then your Z variable converted into T variable. So I don't want to get into that theoretical backgrounds. So of course here as discussion related to that, what do you mean by sigma is known and what you mean by sigma is unknown means. So the population standard deviation is known, we have to use Z distribution or the Z test. So if it is unknown, we have to use T test. So that is the meaning of this. And I hope all of you have the process of hypothesis testing or the stages involved in hypothesis testing. So those steps involved in hypothesis tests are, you have to formulate your hypothesis, both null and alternative hypothesis. Then you should have to select this a test statistic to test your hypothesis, and also you should have to choose the level of alpha, that is the level of significance. Then you have to compute your test statistics based on your sample data. Okay, so after that you have to identify a critical value from your respective distribution table. Then the fifth one is you have to compare your calculated value with the critical or the table value. And the last step is you have to make a decision. So these are the steps which are involved in hypothesis testing. Okay, so hence of course related to the single mean test, when sigma is known, we have to again state your null and alternative hypothesis. And again, there are basic concepts in hypothesis testing along with the steps involved, like null hypothesis, alternative hypothesis, one-sided test, two-sided test, type 1 error, type 2 error, level of significance, and so on and so on. Without having conceptual clarity about these basic or the fundamental concepts in hypothesis testing, I hope we are unable to understand what do we mean by hypothesis testing and how to interpret the results of this hypothesis testing. So with presumption, you have the knowledge of all those fundamental concepts of hypothesis testing, we are discussing these different tests of hypothesis. So now it is a one mean test when the sigma is known. So then the null and alternative hypothesis, for example, is one-sided as like this. Null hypothesis is mu is equal to mu naught. So the first mu refers to the population value. Mu naught refers to your sample value, calculated value. Okay. And your alternative hypothesis is that is the population mean is greater than your sample mean. Okay. Sample mean. So that's why it is left to you whether you should have to test a hypothesis of one-sided or two-sided, right tail or left tail, or within, that is within one-sided or two-sided. That depends upon your research question, depends upon your hypothesis. So for example, so the two-sided test is when you have no clarity or clear idea about the type of the association between the variables, or whether it is greater than or lesser than, higher or lower. So if you are not having any such knowledge, then you have to state your hypothesis as a two-sided hypothesis. If your purpose is to test a hypothesis like greater than, lesser than, higher, lower, more, less. So these kinds of hypotheses, if you want to test, then you should have to have a one-sided hypothesis. So if your hypothesis is to test a greater than, then it is right side test. Lesser than, it is a left tail test. And from this discussion, in short, though of course you are not having, if you are not having much knowledge related to this hypothesis testing, in case of one mean test when sigma is known, Z statistic is this. Z is equal to x bar minus mu naught, okay, divided by sigma by root n. This is the Z statistic, where x bar is the sample mean. Okay, x bar is sample mean. Okay, then the mu naught, of course, sorry, the mu naught earlier I have told you is a sample mean. No, it is the population mean, or what you have hypothesized that. So that's why X bar is a sample average, mu naught is the hypothesized value about your population, and the sigma standard deviation of your population, and the n refers to the number of the observation. Okay, so if your calculated value of this Z statistic is greater than Z alpha means the critical value, table value at your chosen level of alpha. So this chosen level of alpha is the level of significance. So there are three arbitrary values are used in practice, and they are called as 1% level of significance, 10%, 5%, and 10% level of significance. Okay, so based on that choosing your level of alpha, you have to reject your null hypothesis of that is mu is equal to mu naught, or your sample value is equal to your expected value of the population if your calculated value Z statistic is greater than the table value or the critical value. Okay, this is the decision rule which you should have to take. Okay, and in recent years, because of application of statistical packages in research, okay, the earlier method in hypothesis testing, though I have not used that name of the method, that method is called as test of significance method or critical value approach to hypothesis testing. Whereas in statistical packages, that gives one value that is called as p-value, and by making use of that p-value approach, we are able to test our hypothesis. This p-value approach is a kind of testing hypothesis based on the observed level of significance. Observed. So here we need not to assume arbitrarily the level of significance in case of the earlier method at 1%, 5%, or 10%. So exactly this p-value method gives the probability of the truth of the null hypothesis. So if the probability value is very less, then your null hypothesis is not true. So if your probability value is larger, then you should have to accept or do not reject your null hypothesis. So again, I don't want to get into that basic discussions of hypothesis testing. Probably you had already have a class in this course, or otherwise you will have a class on the basics of hypothesis testing. Okay, and related to this p-value approach as a method of hypothesis testing or approach to hypothesis testing, what you should have to keep in your mind as a rule of making decision of reject or not to reject your null hypothesis is given in the last two lines or points of this slide. That is, if the p-value is less than the alpha. So every statistical package give you a probability value. So if that reported probability is less than the chosen level of alpha, for example, you are assuming that you are testing that null hypothesis at 5%. If the probability value is less than 5%, you have to reject your null hypothesis. Otherwise, means if the probability value reported by your statistical package is greater than or equal to alpha 5%, then do not reject your null hypothesis. So just keep these two criteria in your mind, okay, whether to reject a null hypothesis or not based on this p-value approach. So that's why we can test hypothesis actually by three approaches. One, of course, we have not been discussed here, and which is, of course, which is most important theoretically. That is not much used in practice, but in recent years it is used because of the limitations of the critical value approach. Again, I don't want to get into that. That the approach name is confidence interval approach of hypothesis testing. The second one is critical value approach of hypothesis testing. The third one is probability value of hypothesis testing. So now let us take one example for this. One example for testing single mean test when the sigma is known. The problem is a phone industry manager thinks that customers' monthly cell phone bill have increased. Okay, customers' monthly cell phone bill will have increased, and now the average over $52 per month. That means he or she is claiming that, or the manager of the phone industry claiming that the average bill, phone bill paid by the persons or the households is above $52. So now the company has to test this hypothesis or the claim. So that is the hypothesis is that the average mobile or the cell phone bill is more or over $52. So for this claim, we have to state our null and alternative hypothesis. The null hypothesis is a hypothesis which we have to nullify. So hence the claim of the manager is he or she is expecting that the bill value is above $52. Hence your null hypothesis should be opposite to that, against to that. So hence it is less than or equal to 52. So then the null hypothesis is mu is less than or equal to 52 means the average phone bill price is not over $52 per month. And the alternative hypothesis is the claim of the manager. The claim is the average phone bill is greater than $52 per month. Hence, symbolically, it is written as mu is greater than 52. And as a student of, okay, or as a researcher, better to say, as a researcher, you should have to have, or you should have to learn statements in statistics, statements in research work more specifically, both in terms of verbal form, that is in terms of textual form, and also you should also learn how to say transform that verbal or the textual, okay, the statement into symbolic way. That's why the mu is greater than 52 is equivalent to the average cell phone bill is greater than $52 per month. So instead of stating this statement or a phrase or your hypothesis, symbolically it is written in compact, concise, succinct manner, that is mu is greater than 52. You should have to learn all these things as a researcher. Okay, the same of course here is given, and this is a one-tile test, as already I have told you that, because you are testing a direction. So direction is the cell phone bill cost is greater than 52, and null hypothesis is less than 2, so less than 52, hence it is a one-sided hypothesis. And diagrammatically the same can be represented like this, same can be represented this, and let us assume that we are testing this hypothesis at a 10% level of significance. Hence the level of alpha is 0.10 here. Then diagrammatically we can represent that critical region here. And here this do not reject null hypothesis region, where the region which is marked with this blue color, you know, that is the rejection region of null hypothesis. So if your calculated if your calculated value lies in this rejection region, you have to reject your null hypothesis. If it does not fall within this rejection region, means it lies in the do not reject region, hence you do not reject your null hypothesis. And in this process of hypothesis testing, in all the tests of hypothesis, earlier I have told you that there are two values. One is calculated by yourself, the other one is given by the table. The table value is called as critical value. For example, for 10% of level of significance, the Z table value is 1.28. So how you should have to obtain? You should have to obtain this value from the Z distribution table, normal distribution table. So then you have to simplify your answer, or you have to calculate your Z value. Okay. Now in continuation of our discussion, let us assume that we have obtained the results related to that earlier claim of the phone industry manager. So let us assume that we have selected 64 persons, and the average monthly phone bill of this 64 person is 53.1. So which means we have collected information from the 64 persons regarding the monthly phone bill, and the average for this 64 person is 53.1. This is called as X bar sample mean. And as we already noted that we are assuming population standard deviation is given and the population standard deviation is already known and it is 10. So we need 3 elements to calculate Z statistic. One is number of the observations, the second one is X bar, and the third one is sigma value. So all 3 are given to us. Just assume that now we have substituted all these 3 values into our Z formula, that is Z is equal to X bar minus mu naught divided by the sigma by root n. So that's, if you simplify this, that gives 0.88. This 0.88 is known as calculated value of Z, computed Z value, computed Z value or observed Z value. So these are the synonymous names. So now you have to compare this observed value, calculated value, computed by yourself with the table value. Earlier, we have noted that the table value for 10% level of significance is 1.28. 1.28. So now this slide shows you a diagrammatic representation of decision. So the decision is whether you do reject your null hypothesis or do not reject your null hypothesis. Since your calculated value, from that your sample evidence of X bar is equal to 53.1 and the standard deviation of 10 and with a sample number of 64, your calculated value already we have noted that it is 0.88, but the table value is 1.28. Since your calculated value, that is the computed from your sample data, is less than the table value, you do not reject your null hypothesis or you cannot reject your null hypothesis. Hence, do not reject your null hypothesis because Z value of 0.88 lies in do not reject the null hypothesis reason or less than 1.28. So hence from this discussion, how to make decision about rejection or not to reject your null hypothesis is that if your value, computed value is less than the table value, do not reject your null hypothesis. Otherwise, means if the value calculated by you, irrespective of the test, not in Z1, Z is one, only in Z, you can reject your null hypothesis. So hence, do not reject your null hypothesis since 0.88 is less than 1.28, and that means that the result of this discussion or the result of this hypothesis testing is that there is no sufficient evidence that the mean bill is over $52. So that means that the claim of that manager is not correct. That means on the average, okay, the households in that particular city spent only $52 per month as their cell phone bill. So this is the way which you should have to finally provide your conclusion related to hypothesis testing. So this is about a single hypothesis mean test, single mean test in simple words, when sigma is known. But when sigma is not known, it is the probability value approach. I don't want to get into this. Okay, then now it is a two-tailed test. Again, I don't want to get into this. The procedure for estimation and others, it is same, but only difference in case of the hypothesis statement. Earlier hypothesis test is called as one-sided single mean test, and this is called as two-tailed or two-sided single mean test. The claim is that on the average, that is the mean number of the TV sets in US homes is equal to 3. That is on the average, every home in US having 3 TV sets. Alternative hypothesis is no, not equal to 3. That's why null hypothesis is mu is equal to 3, whereas the alternative hypothesis is mu not equal to 3. That means this is a two-tailed test. And here also, you have to select a level of significance. For example, here it is 0.05 level of significance has been chosen, and the sample size here is 100. Okay, 100, that is 100 house homes. 100 homes have been selected for testing this null hypothesis. Okay, hypothesis. And in case of this two-tailed test, earlier you have only one side of your rejection reason, but now you have two sides of critical values or the rejection reasons. One in the left side, the other one in the right side, because your answer might be greater than 3 or lesser than 3. If it is lesser than 3, so then the right side value comes. If it is less than 3, the left side value comes. So hence it is called as a two-tailed test or a two-sided test. And again, so the next procedures are one and the same. So if you just input all those values into that formula, because the formula is same, there's no difference in the formula, only claim is different, hypothesis is different. So the calculated value of this okay problem, z value is minus 2.0, but the table value is 1.96 as plus 1.96 and minus 1.96, but your calculated value of minus 2.0 is more negative than 1.96. Hence, you should have to reject your null hypothesis. So once you have rejected your null hypothesis, which means that your results are statistically significant. This is another word which you should have to use in your analysis. So if you are rejecting your null hypothesis, means that your results are statistically significant. So if you are not able to reject your null hypothesis, means your results are insignificant. So this is the way which you should have to interpret the results. So since the in this case, the calculated value is more negative than the table value of 1.96, the rejection means that, so that means the number of the TV sets, okay, in US homes is not equal to 3. It might be greater than 3 or lesser than 3, because we are not able to say doing this hypothesis, because it is a two-sided hypothesis. Okay, this is about single mean two-sided hypothesis. Okay. And when this sigma is unknown, thus far we have assumed that the standard deviation of the population is known, and we just use that standard deviation value in our calculation and solve the problem. But if the population standard deviation is not known, so then we have to get or calculate that standard deviation from its sample counterpart. The sample counterpart of the population standard deviation is sample standard deviation, and I hope the notation used is known to you for that standard deviation in the sample, that is yes. That's why only the difference here is instead of z, instead of sigma, now we have replaced it by s. But once you have replaced s, you replace the sigma by s, the variable changes. Earlier we have a z variable, now we have a t variable. That means because of replacing that sigma by sample standard deviation, yes, so the distribution changes. Now you have to use t distribution. So that's why when the sigma is known, you have to use z distribution. When the sigma is not known, you have to use t distribution. That is the only difference in terms of this unknown one. So if the sigma is unknown, means along with mean x bar, you should also calculate s for computation purpose. So in practice, what we have to do additionally, we have to also calculate standard deviation for ourselves, for the data at our hand or the sample observations. So, and within, of course, within this, you can do it as a one-tail test or two-tail test. Okay, again, I don't want to get into that. For example, here it is two-tail test. Okay, that is because alternative hypothesis is not equal. One tail means it is greater than or lesser than. Here we have one more example for this population standard deviation is unknown, and also the test is two-tail or two-sided one. The average cost of hotel room in New York is said to be $168 per night. Okay, to test this hypothesis, 25 hotels are selected, and the average sample average has been calculated. The sample average means the sample average cost of hotel room in New York for 25 hotels is $172.5, and the standard deviation we have calculated. I hope you know the formula to calculate standard deviation from the statistics. You have to use that knowledge of calculation of both x bar and y if you want to manually do this. Otherwise, if you use computer packages or statistical packages, you need not to do all these calculations. Only final results are given to you. You have to interpret the results. Okay. So let us here consider these are the calculated values. Now we are testing this hypothesis of $168 per night room cost in New York City with a 5% level of significance. So for that, we have to do all these calculations. Finally, we will arrive at a calculated value of 1.96. 1.46. So now this is your calculated value of the t, and again the procedure is same. Even in case of t test, you have to compare this t value of calculated by you with the table value at 5% level of significance. And one more word that comes is the degrees of freedom. Degrees of freedom. So along with the degrees of freedom, you have to identify the table value. The table value for this 24 degrees of freedom is 2.0639. Okay, but your calculated value is 1.46. Your calculated value of 1.46 is less than the table value of 2.06. Hence, you cannot reject your null hypothesis. Means not sufficient evidence that true mean cost is differ from 168. That means the average cost of the rooms, the hotel rooms in New York City is $168. That is the final conclusion. So hence, whether you have a one-sided hypothesis or a two-sided hypothesis, okay, the procedure is same. The procedure is same, and in all these cases, you will get one calculated value. You have to compare your calculated value with the table value. So this is about one mean test. One mean test. As just earlier, I have told you that this is not much used in practice, because always in practice, our purpose is to compare or to find a difference or to compare the difference or to explain or analyze the associations among the variables. For that, at least we should have to have two or more than two variables. So if our purpose is to compare the mean values for the two populations, two samples, then we should have to use two means test. Okay. So if you have only one population, we have drawn one single sample from that and tested hypothesis in earlier discussion. So now we have two populations. So let us assume that we have two groups of people. So for example, so the impact of a government program on the people in a particular area. So then you have two groups of people. One are the persons who are affected by that particular program. They are called as beneficiaries. And the other group is called as non-beneficiaries. Okay. They are beneficiaries and non-beneficiaries. Now we have two groups of people. Okay. Then whether the particular program affected on that or not, you are able to measure that in terms of your selected variable. For example, the income of that people, or the consumption expenditure of that people, standard of living of those people, or the assets of those people, that is the beneficiaries and non-beneficiaries. Now you have two populations, or your purpose is to compare the income, okay, of two, that is the two kinds of peoples, or the two kinds, or the two groups of peoples, or two cities. That is the average income of peoples of Mysore and the average income of peoples or the households in Bangalore, or average house of average consumption expenditure of households in Davangere and in Shimoga. So, or you are intent to compare like that income, consumption expenditure, price of two commodities, or demand for two commodities. So you can choose any economic variable, and your purpose is to compare that economic variable between the two people in terms of its average, in terms of their averages. So in such cases, we have to use two population mean comparison test. So in this two population comparison mean test, as just we were earlier noted, that we have to select the appropriate tool or a test based on whether the two populations are independent or dependent. If the two populations are independent, we have to use independent sample t test or z test. If the populations are dependent, we have to use paired test or matched pair test. So the dependency means the populations which have been selected are related, dependent. So more specifically, that a dependent related kind of test is easy to identify when you have an analysis related to before, after, pre and post. Whenever you have a data or your purpose to analyze the before and after effect, pre and post effect, then the variable is dependent, related. So then you should have to use paired test or matched paired test or the dependent sample test. This is the idea which you should have to be there in your mind before getting to two population means test. And just as I already told you that, of course, the purpose of these two populations comparison is different. One is our purpose, of course, thus far we have noted that we are testing or claim our claim of our hypothesis in terms of the mean only, So if you are interested to test the proportions, you can also use these tests for testing proportions. And also you can use these two population for test for variances. Then they are called as population proportion test, then two population variance test. But I don't want to get into that proportions and variance test. So only the difference is in the formulas are same almost. Procedure is same, but the purpose is different. And just as I already told you that these two sample tests are classified based on the purpose, and population mean test in case of matched pairs, population mean test in case of independent samples, then the population proportion test comparing proportion of first population with the second population, and the first population variance with the second population variance. So these are the theoretical underpinnings which you should have to bear in your mind in selection of these two sample tests, or more specifically two sample mean test for our discussion. And of course, the testing the two populations for mean values means like this. Your null hypothesis is the mean value of the two populations are identical. I hope these two distributions, okay, the peak of these distributions are the same. Okay, so the middle of this distribution is the mean value. So hence the middle of these distributions are identical. Hence there is no difference in the mean values of the two populations. That's why the average consumption expenditure is same, no difference. Average savings are same. The mean consumption expenditure is same. Mean income is same. Mean price of those two commodities are same. The mean or the average sales of the two companies are same. Like this, you can take any variable. Okay. So your hypothesis, null hypothesis is there is no difference in the mean value of the two populations related to your selected variable. But the alternative hypothesis is there is a difference. So again, if there is a difference, means it is a two-sided test. So the first population mean or the average is greater than the second one is one-sided test. Or the second population's mean value is less than the first population mean value. So this is also a one-sided test. Okay, so the diagrammatically that can be seen like this, because whereas in the second alternative hypothesis, so if you, for example, the peak of this purple distribution is this, whereas of this green is this, so then the mean values are not one and the same. There is a difference in the mean value. You are testing whether the difference is significant statistically or not. So this is the theoretical underpinnings related to this two sample mean test. And related to this two sample mean test, there are different things we should have to bear in our mind. And of course, one point we have already noted is whether we are testing two means for a independent samples or a dependent samples. Okay, that is the first one. The second one, if you take, for example, the first independent sample test. Okay, in that independent sample t-test, again we have to have answer for several queries, sub-questions, like whether the population standard deviation is known or not. As already we have noted that if the population standard deviation is known, we have to continue with the Z test, even for the two population mean test for the independent sample or even for the dependent sample also. If the population variances are not known, we cannot use The Z-test, as we already noted in single mean test, we have to rely on the t-test. Within this t-test, again, we have two issues. The one is whether the variances are equal or whether variances are unequal. So that is, the variance of the two populations are assumed to be equal, or the variances of the two populations are assumed to be unequal. These are the theoretical issues, okay? Because if we have these circumstances or situations, we have a separate procedure of calculations. So I don't want to get into that part of calculation. So it is only a theoretical underpinning related to two mean test. So Z-test is used when sigma of both the populations are used. And if it is not known, we have to use t-test as usual in case of the earlier analysis. But within t-test, whether we have to test or we have to assume the variances are equal or unequal. Okay, these are the assumptions. Earlier we already noted that. And this is the formula we have to use in calculation of Z-test when the sigma is known. That is, the variances of the populations are known or the standard deviations of the populations are known. So just the formula is extended. Earlier you have x bar minus mu, Now you have two variables, x and y. So your purpose is to compare whether x bar and y bar is statistically significantly different or not. That's why the first element in the numerator is x bar minus y bar. That should be the difference should be subtracted from your population expectations, hypothesis. So the null hypothesis in all these cases is there is no difference in the mean values. Then this becomes 0. And the denominator is variance. Variance of x variable and the variance of the y variable respectively divided by their number of observations, and you should have to convert it into in terms of a standard error. That you have taken a square root for this. And this is the formula to calculate the test statistic, Z statistic, if the sigma is known or sigma square. Variance or standard deviations are known. Okay, the same, of course, is given here. And one more, again, in continuation of the hypothesis testing, you can, even for the independent samples, earlier I have told you that you can have a hypothesis of two-tail test, one-tail test of lower tail, that is the left tail, or upper tail, or a right tail test. Then how to define or symbolically represent our hypothesis is in this form. That is the similar. And the meaning earlier we have already noted that. So what do you mean by two-tail test? This is the rejection regions are appear in the two sides, whereas in case of single side, if it is an upper tail in the right side, lower tail in the left side. So the area which are marked are known as rejection regions of that hypothesis testing. And if the population variance or the standard deviations are not known, but variances are assumed to be equal, then of course we have to use this formula. The SP is called as pooled variance test. Okay, this is called as pooled variance, and only the denominator is somehow changed. Okay, this is S means S square means pooled variance. Pooled, that is the pooled means variances of the two populations. That's all. So this is the formula. Then how to calculate this pooled variance? By this formula. Okay. So then if the variances of the populations are assumed to be unequal, then we have one degree of freedom that is called as V, and we have to calculate this V by using this formula. Okay. And the final formula is only like this, or only like this. So that's why a discussion thus far we have related to this independent sample t-test, independent sample test using Z, using T, using Z when sigma squares are not, using T when sigma squares are not known. Within using T, whether the variances are assumed to be equal, whether the variances are not assumed to be equal or unequal. So these are the points which we should have to bear in your mind in testing hypothesis of independent samples. And of course, here we have one example for this test, t-test. So that is when variances are assumed to be equal. Now we are comparing, okay, the difference in the prices of the two stocks, are the dividend yields between the two stock markets, that is the New York Stock Exchange market and Nasdaq. Okay, and final values are given to us. That is, the sample mean is given to us, sample standard deviation given to us. If they are not given, we ourselves has to calculate them. Okay, calculate them. Okay, so then the number of the shares or the stocks are 21 from NYSE and 25 from Nasdaq. Okay, by using this information, okay, as a financial analyst of a brokerage company, okay, he or she has to identify, is there any difference in the dividend yield of these two markets? So if there is a difference yield of the dividend, then he or she has to suggest there is a significant difference in the yield, and that brokerage company has to invest its investment in the higher dividend company. So to answer for this question, we should have to conduct a hypothesis for this, and we are testing this hypothesis of no difference between the dividend yield of these two markets, okay, stock markets, with 5% level of significance. So these are the manually we have to calculate, otherwise our statistical package is given us. So this is the final calculated value of our T is 2.04. This is the calculated value of the T. So for okay, 44 degrees of freedom. Okay, 44 degrees of freedom, because the total we have 21 plus 25, 46, minus 2, it is 42 degrees, 44 degrees of freedom. The table value is 2.04. Okay, 2.0145. Okay, table value is 2.015, whereas the calculated value is 2.040. So 2.040 is greater than 2.015. Hence, we have to reject our null hypothesis, and the conclusion is that there is evidence of difference in the mean yield of dividends. Okay, the dividends of this Nasdaq and the New York Stock Exchange market are not one and the same. That is the inference or the conclusion which we can draw from this one. Okay, this is about a two means test for independent samples. Okay, since of course we have already spent more than 90 minutes. Dr. Uchegoda or Chetan, shall we have a break at this point for 10 minutes?
Yes, sir. Yes, sir. We can have a break, sir. Just let's. I mean, if you give permission, we can just ask the participants to raise any questions if they have any, sir.
Okay. They can. If they have any doubts, they can ask for a few minutes. Then we will have a break after that.
Yes, sir. All the participants. All the esteemed participants, if you have any doubts or something, you can raise your queries to the professor, and you are actually allowed to unmute yourself and raise the questions. You can unmute yourself. Permission is actually granted. If you have any questions or queries, you can raise the same to professor.
Hello.
Hello, sir. So I don't think any participants have any queries. Okay, there is one. Yeah, Jayaprasad, sir.
Yes,
yeah,
sir.
please.
Hello.
Yes, sir, please.
Sir, good morning, sir.
Good morning.
Sir, you explain with the parametric and the non-parametric test, sir.
Yeah.
Hello.
Hello, yes, please. Audible. Please continue.
Sir, you explain with both the test parametric and the non-parametric, sir. Sir, in what basis they have to distinguish between both the two, sir?
Okay.
Based on population, or it should be directly we can connect with the Z or F test or chi-square like that, sir. In what basis you have to distinguish, sir?
Okay. First thing, as we already noted, that the first condition for use of parametric test is that your selected variable or variable should be follow normal distribution. So hence you should have to first test whether your selected variable is normally distributed or not. So if your selected variable is not normally distributed, you cannot continue with parametric test. Okay, this is the first criterion. The second one, if the variances of your populations are not independent, okay, or means, as we already noted, that the second condition is if they are dependent, then the parametric tests are not much useful. Okay, then the third and the most important, okay, one and the best criterion when you should have to select a parametric or non-parametric is if your variables are continuous variables like interval or ratio scale variables, you have to use parametric test. If your variables are ordinal or nominal variables, you have to use non-parametric test. Okay, you just rely on the third one. That is, if your variables are nominal or ordinal variables, use non-parametric test. If your variables are parametric, if your variables are quantitative, like interval or ratio scale, you have to use parametric test. That is the best criterion to decide which you should have to use.
Sir, meanwhile, one more question, sir.
Yes, please.
When we are framing for the questionnaire designs and everything, we are commonly go for the Likert scale. Is it right now, sir?
Yeah.
Yeah, but sometimes they are using with a dichotomous question also. Which is the result is best according to your way, sir, your opinion for that?
Okay, for example, you have said Likert scale. The Likert scale is an ordinal scale. Actually, the variable is ordinal variable. Okay, so for those ordinal variables, theoretically, non-parametric tests are better, but in practice, parametric types of tests are also used for that. But for theoretical reasons, if you are using a Likert scale, then you have to use non-parametric test for testing hypothesis. If your collected informations are dichotomous, like yes or no types, then you cannot use. That is, yes or no is like a purely nominal variable. Okay, for that yes or no are a dichotomous, or even for a multichotomous, where you are unable to order your variables or measured even in terms of your Likert scale, purely you should have to use nominal type. That is the non-parametric for that. Okay, for Likert scale, it is an ordinal variable. Non-parametric is theoretically appropriate, but for dichotomous or multichotomous variable, purely nominal it is, and hence it is non-parametric test.
Okay, thank you, sir. Thank you.
Okay.
If any other participants have any queries, you can raise the same to the professor.
Otherwise, also you can send your queries through the chat, and we will have that related discussion at the even end of our session in the next session.
Okay, so sir, actually one query on my part, sir.
Yeah. Yes.
Sir, actually, like what I personally feel is, I mean, when we are actually speaking about an econometric tool or something, it is very much pertinent that we understand how to use it, as well as even we should be having the rationale behind when to use it and why to use it.
Yeah.
So in this backdrop, I mean, just out of curiosity, I'm just asking.
Okay.
Thing is, like, while we are actually giving examples, in that examples, you actually gave an example of the television sets in America, like more than 3 or less than 3 or something like that. So in that context, I mean, the theoretical rationale and how to use the t-test for the said this thing, I understood that.
Okay.
Now, I mean, as far as I'm concerned, when we are actually using econometric tools or econometric models, it is actually there to substantiate, and ultimately it must result in some policy formulation or something like that.
Yes.
So here, when I'm actually using, I mean, I just wanted to know, why would I be interested in knowing like whether Americans have like more than 3 or less than 3? Like in the greater picture, like if in the greater wholesome picture, what would be the relevance of me getting this data?
Okay. But so that the tools thus far we were discussed is they are not econometric tools. They are pure statistical in nature.
Okay, sir.
Okay, that is the first one. The second one is that so just I have taken that as an example. Okay.
Yes, sir.
As that is given in one statistics book written by Newbold and Carlson and others. So just I used those PPTs here. So That is an example, but you can use any. These tests are thus far we were noted, and the other tests which we will take in the next session also. They are the fundamental hypothesis test related questions. That means our purpose here is just to compare the mean of a population, comparing the means of the different populations, whether there are significant differences in the mean values or not. So they are called as classical type of hypothesis testing with some fundamental objectives. But when we get into econometrics, in all our econometric analysis, our purpose here in econometrics is to measure cause and effect type of relationship. So in testing those hypotheses, whether that particular variable influences or not, whether that influence is statistically significant or not, if it is statistically significant, what its relevance in practice and how to interpret that result and what is the policy relevance of that. So they can all be discussed in cause and effect type of relationship. But in these hypotheses, we are not measuring the cause and effect type of relationship. Okay. For example, if you take, for example, I have given one just a few minutes back, I have given an example comparing the dividend yield of two markets. It has also a policy implication. Because as a analyst, financial analyst in a brokerage firm, you have to answer for that brokerage firm where it should have to invest its money, whether in Bombay Stock, in the New York Stock Exchange or in the NASDAQ. So one of the simple, statistical tool is this. That means if the National Stock Exchange provides higher yield and which is statistically significant compared to NASDAQ, then your final policy option is, so you have to suggest your company or that brokerage firm, so the company has to invest in New York Stock Exchange than in NASDAQ. So that's why even by using these simple statistical tools, you can say suggest policy or you can evaluate the policy. For example, if you take say the women empowerment related programs, the impact of that is SSG on women empowerment, more specifically economic empowerment. So in such cases, one of the simple analysis is the beneficiaries are the members of the SSGs and the non-members of the SSGs. So if you select the variables like the average income of beneficiaries and non-beneficiaries, average consumption of beneficiaries and non-beneficiaries, and average savings of beneficiaries and average savings of the non-beneficiaries. So it is an independent sample t-test. By using that independent sample t-test, you can evaluate whether that SSG program is succeeded or not. By if all these indicators, just I have told you as measurement indicators for economic development of or economic empowerment of the woman, if they are higher statistically or significantly different with the non-members who are not the member of the SSGs, then that program has been succeeded. So in this way, you can, by making use of this simple hypothesis testing, so we can evaluate the programs and even we can suggest the policies either to the government or to the companies. But these hypothesis testing thus far we were noted, they are not at all given any reasons why that is higher, why the other one is lower, what are the reasons for. All these things cannot be answered by doing all these things, and for that purpose we need to test hypothesis doing econometric analysis, or more specifically the econometrics is nothing but using regression analysis. So to answer for the questions like why and how much, so only we are able to answer for this question of why and how much only by using regression analysis or econometric tools. So hence these illustrations are also the policy relevance as a simple statistical tools. So this is my response to your query. I hope I answered your question.
Yeah, thank you very much, sir. Thanks.
Okay, welcome.
As Professor already pointed out, if any other participants have any queries, they can actually post via chat or via WhatsApp group. And so we would be taking breaks. How much time would you require, sir?
10 minutes. Now it is 11:50 around. So
okay,
we will rejoin at 12 o'clock. Huh?
Fine, sir. So as the professor informed, the session will resume at 12 p.m. We request all the participants to come online by 12 p.m. Thank you very much, sir. Thanks, sir.
Thank you.